This is lecture 30 of Condensed Matter Physics 1. And in today's lecture, I am going to discuss effects of anharmonicity in the potential between two atoms in a crystal. So, let me remind you that what we have done so far is that considered the potential to be harmonic. So, the form it has is 1/2 some k u j plus 1 minus u j square, which I am going to write as 1/2 k x square. So, the form this potential has is like this. If I plot it with respect to x, it appears to be purely a parabola. However, recall how this is obtained. If I take these atoms to be at equilibrium, then the force on each atom, which is minus dV by dx, is 0. So, if I expand the potential V x about this equilibrium point, this is going to be V x 0 plus the first order is going to be 0, because the first derivative of the potential is 0, and then you get the second order, which is 1/2 V double prime symbolically as x minus x naught square, plus then there are going to be these higher order terms, 1/6 V triple prime x minus x naught cube plus raised to 4, and so on. What is the effect of these terms on the system? And the effects are very important. For example, if V was only harmonic, that is, V x was of the form 1/2 k x square, then for V x being harmonic, there will be no thermal expansion. In the crystal, and there will not be any thermal resistivity, that is, thermal conductivity will be tending to very large number without anharmonic terms. So, this is what we are going to focus on, these two things, how anharmonicity gives rise to these two effects. Our discussion is more qualitative and focuses on ideas and looks at general trends of these two properties. A more precise calculation can of course be done, and that requires a little more sophistication. But the general ideas are precisely what we are going to discuss here. So, let us look at thermal expansion first. So, if the potential was purely harmonic, then it looks like this. This is with respect to x, this is V x, and this is half k x square. If I have an atom vibrating in this system, as the temperature is raised, it goes to higher states, but still oscillates symmetrically about the origin. So, on an average there is the no expansion, the average x remains unchanged as temperature rises. Now, how do I take it to a lattice? As in a crystal, we have these atoms connected and have some equilibrium distance A. So, this x is representing the change in A. This is x. So, what we are saying is that if with respect to x the interatomic potential is harmonic, then there is no expansion. The general distance remains, average distance between the atoms remains the equilibrium distance. So, in the absence of anharmonicity, average distance between atoms is equal to A, where A is the equilibrium distance, no change. Now, let us see how anharmonicity affects it. So, as we said, we are going to write V x as equal to, I will ignore the constant term, the harmonic term of 1/2 k x square. Then I could have plus or minus the anharmonic term, the coefficient I am going to call g, x cubed, plus higher orders, which could be x raised to 4, x raised to 5, and so on. And we are going to assume that g is much less than k. So, primarily the crystal is harmonic, but there are these terms, and let us see how this changes the potential. So, if I take g to be positive, so that is the potential to be 1/2 k x square plus g x cube. Without the g x term, the potential would have been something like this. And when you include this term g being positive, so we are taking g to be greater than 0, it becomes larger on the positive side and less on the negative side, and probably at a very large distance it will flip, but this is how the potential is going to look. On the other hand, if I have the potential to be 1/2 k x square minus g x cubed, G is still greater than 0, then the potential is going to change the other way. Is going to become larger on the negative side and then less on the positive side, or a little softer. So, as you raise the temperature here, this is what is going to happen. And on the right hand side, this is what is going to happen. What you notice is that the average distance between the atoms is increasing in the second case. Let me make it with a different color. This is green, shows the average distance, and here is decreasing. So, in this case, average distance between atoms is decreasing, and here average distance between atoms is increasing, and this is thermal expansion. So, I have given you a qualitative idea as to how inclusion of x cube terms with a negative correction makes the system or the crystal expand as temperature is raised. Let us now make it a little mathematical. Before that, let me just give you a question. How will the next order anharmonic term, that is 1 proportional to x raised to 4, affect the size of the system with temperature? So, let us now do mathematical analysis. So, for these atoms, again let me remind you that x that I am writing is the change in the distance between the atoms. So, this they are at a distance a, and we are changing this by x. Then the probability that displacement is x, that P x is going to be proportional to the change in the energy from the equilibrium position. So, that is going to be half k x square minus g x cubed divided by k B T. And therefore, average x is going to be equal to integration minus infinity to infinity. I am calculating the value of x. So, this is P x dx divided by integration minus infinity to infinity P x dx. By the way, this discussion is based on Kittel chapter 5. And again, let me remind you that we are taking g to be much less than k, and therefore, we can make certain approximations. So, I am going to write e raised to minus 1 half k x square e raised to minus, it will become plus g x cubed as e raised to minus 1/2 k x square times 1 plus g x cubed, and stop there, and we stop at cubed. And therefore, average x is going to be integration minus infinity to infinity x e raised to minus 1/2 k x square plus g integration x raised to 4 e raised to minus 1/2 k x square, or divided by k b t divided by k b t divided by integration minus infinity to infinity e raised to minus 1/2 k x square over k b t dx plus minus infinity to infinity g x cubed e raised to minus 1/2 k x square over k b t dx. That is the average value of x. Now, integration minus infinity to infinity e raised to minus 1/2 k x square over k b t is equal to square root of 2 pi by k k b t. Square root of x raised to 4 e raised to minus 1/2 k x square over k b t is equal to 3/4 times 4 k b t over k whole square, square root of 2 pi over k k b t, and the terms x e raised to minus and x cube e raised to minus, minus infinity to infinity, minus infinity to infinity, this is minus 1/2 k x square over k b t minus 1/2 k x square over k b t are 0 because they are odd integrands. So, we are left with two terms, and therefore, we get average x equals, the first term was 0, the second term I think I forgot it in the last slide, it is g over k b t times 3/4 times 4 k b t over k whole square times that square root term divided by the square root term. The square root term cancels, 4 cancels, and you get average x to be equal to 3g over k square times k b t proportional to t. So, the average distance between the atoms in the crystal changes with t, and this change is proportional to t. So, we are given a qualitative argument based on the anharmonic nature of the potential between atoms, that the change in the distance is going to be proportional to t, and this coefficient here is the coefficient of thermal expansion. This is what shows you that x cube term that makes the potential asymmetric is responsible for the expansion. A rigorous quantum mechanical calculation requires calculating the change in the volume of the crystal with temperature using its equation of state, which we are not doing, but the basic idea has been given. So, the rigorous treatment requires getting the equation of state for the system. So, one would calculate its free energy, one would calculate the pressure and then see how much work is to be done when the volume is changed and so on. And for that, if you are interested, a good discussion is in Mermin's book. So, this is as far as thermal expansion of systems is concerned. Next, I will discuss thermal conductivity. And I begin by describing an experiment. So, this experiment is taken from, the data is taken from P. D. Thatcher, which is in Physical Review, volume 156, page number 975, and this is taken in from 1967. And let me show you what the data shows. It plots thermal conductivity copper in terms of joules per meter per Kelvin, and it is on the logarithmic scale. So, let us say this is 0.02, then you will get 2, then you will get 20, then you will get 200 times 10 raised to 2. And here you have the temperature 10, let me make 10 here and 100, and then it increases. So, this is the temperature in Kelvin and conductivity. There are 4 different samples and this is how it goes. You plot it, and for a large size sample, this is how it is going to change. This is of width 7.25 mm. Next, a sample of 4 mm is taken, and it goes parallel to this, but does not go as high and then merges with this curve. This is 4 mm size. Size is further reduced, and at 3.14 mm, this goes further down, line is still parallel and then merges. So, this is 3.14 mm. And finally, 1.06 mm curve goes up like this, and then at higher temperature goes like this. I am not able to replicate exactly the curve shown, but if you are interested, you can look up this paper and see what happens. The important point is that the thermal conductivity copper depends on the size scale of the sample. That is point number 1. And in fact, in the same paper, if you plot, and this plot is given in the same paper, k over t cubed, versus the size d, what one sees is that this line is a straight line. And this is at low temperature, here low temperature. So, what one concludes from this is that thermal conductivity kappa at T tending to 0 at low temperatures is proportional to d, the width of the sample. So, that is something we would like to understand. Other thing is this line is straight. So, let me go to the next slide and I will just show one of the curves. So, if I look at this curve, this is kappa versus T, this line out here is straight and then it goes like this. This is a straight line. And since this is log scale, so you have log kappa is equal to some number n log t, or kappa is proportional to t raised to n for t going towards 0. And this value of n is 3. That is point number 2. Point number 3 is that as temperature goes high, you have log kappa proportional to some constant over t, log of constant over t. Sorry, this is constant over t. So, kappa seems to go as some constant over t, and somewhere here this is kappa is like e raised to c over tau. So, at high temperature out here, let me make it here, it goes like this, the slope is -1. So, here ln kappa is minus log t. So, kappa goes as c over t, and somewhere in between it is like this. So, we got to explain all this behavior. Before that, is this behavior universal? Let us ask that question. Is this behavior universal, or we are just seeing it in, this was for LIF. So, if you plot kappa versus T for sodium fluoride, here also highest goes to about 200 times 10 raised to 2 joules per meter per Kelvin. This also shows similar behavior. And Furthermore, if you make sample purer, this is taken from Jackson and Walker, Physical Review B, volume 3, 14/28/1971. And if you take samples with different purities, you also see that as purity improves, this is better purity, and this is for germanium. Copper goes up, this is about 50. This is taken from Jibal and Hull, Physical Review, volume 110, 773, 1958. So, what you notice is we have already noted that at low temperature conductivity goes up as a power of T raised to 3. It is proportional to the size of the system, and as you go to higher temperatures, it changes behavior. It starts coming down as exponential, some constant over T, and then finally at very high temperatures it goes as 1 over T. We need to explain all this. So, let us write this general behavior first, and then we will try to understand this. One, at low temperatures, kappa is proportional to D, that is the size of system. 2, at low temperatures, kappa is proportional to T cubed. So, you can say by combining these two, we can say that the thermal conductivity goes as T cube D for T tending to 0. Third, as T is increased, K increases, or kappa increases, and then it starts decreasing as exponential some constant over T. Four, at temperature going to very large, and I will explain in a minute what large and small means. This conductivity appears to go as T inverse, and finally, purer the sample, higher the conductivity. So, to understand this, let us look at kinetic theory and analyze the behavior of K in terms of different quantities appearing there. So, kinetic theory tells me, and this we have used in the past, that the thermal conductivity kappa is going to be 1/3 C, let me write C V. This is some speed L times L, where C V is the heat capacity or specific heat, of the sample. V is the speed of heat carriers, and L is the mean free path of carriers. So, we got to analyze each one of them and see how they give rise to the behavior that we are seeing. Now, keep in mind that the materials we have shown are lithium fluoride, sodium fluoride, germanium. These are all insulators, and that means no conduction by electrons. If there is no conduction by electrons, what takes the heat from one side to the other? So, question is what takes the heat from higher T side to lower T side? And the answer is that these are atomic vibrations. And now that we have quantized them, we are going to say that phonons are the carriers of heat. Just like when we considered metals, it was electrons that were carrying heat from one side to the other. Now, we are going to take the phonons that are the carriers of the heat. So, if I have the sample at temperature T1 and T2 at the two ends, where T1 is greater than T2, then the atoms on the left hand side are really doing motion with large amplitude. So, the amplitude is quite large. Let us show it by this big arrow. And on the other side, they are cooler. So, motion is less with smaller arrows, and in between the middle size arrows. So, what happens is that the vibrations start vibrating the next layer of atoms, and therefore, the energy gets transferred this way. In the phonon picture, what is happening is that I have these phonons moving around, and the energy of phonons out here, average energy E average, is greater than E average here on the right hand side. This is T1 and T2. Then also higher K values are excited. Here lower K values are excited. And therefore, on the left hand side, V is larger, V is smaller, and therefore, these phonons start going from left to right. Just like in metals, electrons start going from left to right and start carrying energy. So, more phonons are being created and they go from left to right, carrying larger energy, and therefore, net result is that the energy is being transferred from left to right. So, we are going to look at this phonon picture, and what limits the energy transfer? So, the picture we have is that these phonons, higher in energy, lower in energy, they start carrying energy to the side, and what hinders or impedes the transfer of energy. That is, it gives rise to resistivity, and that is scattering of phonons. Just like in case of electrons, the scattering of electrons from impurities gave rise to the lessening of thermal conductivity or electrical conductivity. In the present case, phonons carry no charge, so only thermal conductivity is going to be there. If they get scattered, then that stops, impedes the transfer of energy and limits the conductivity, and that is what's going to be the limiting factor in terms of conductivity of the system. So, I have this conductivity equals 1/2 CV VL, and L is V times tau scattering. So, thermal conductivity kappa is going to be 1/3 CV V square tau, either this or the upper one. So, let us see what happens at low temperatures. This we have done last week, that C V at low temperatures is some constant times T over theta d by cube for T tending to 0. And this constant is roughly 1940 T over theta d cubed joules per mole per degree Kelvin. Let me give you this question here. Show that the constant is indeed 1940 joules per mole per degree Kelvin. And V is V sound. What about L? L is going to be of the order of the, not just order, L is going to be of the same size as the width of the sample, if there is no other scattering mechanism, and we will see that there is indeed no other scattering mechanism. So, what is going to happen is that you have C V equals 1940 T over theta d by cubed joules per mole per degree Kelvin, V equals V s, and L equals the size of the sample, and therefore, the thermal conductivity is going to be 1/3 times 1940 T over theta d by cubed V sound times d, which is 647 T over theta d by cubed V s d watts per meter per degree Kelvin. So, at T goes to 0, kappa is proportional to T cubed, and kappa over T cubed is proportional to D. So, low temperature behavior is explained. Behavior of kappa with respect to T and size D is explained. Very good then. Then why doesn't the conductivity keep on increasing? So, let us see what are the other scattering mechanisms. So, here we consider mechanism by the sides of the sample. The sides of the sample, and no other mechanism. So, if this was the case, what one would expect is that this will go as T cubed, and then as one goes up, it should actually become a constant, because C v goes to a constant. V may go down a bit, so it may go down a bit, V goes down, but some constant, and D is D. So, this is the behavior one should expect. This, by the way, the scattering due to the sides of the sample is known as boundary scattering. So, this T cube behavior is due to boundary scattering. So, if that was the case, this is the kind of behavior one expects. But what we saw was that this fellow comes down like an exponential. What causes that? And that is the next mechanism that we are going to see, and that is where the anharmonicity of the crystal comes into play. So, question is that boundary scattering would have given this T cube behavior, and then one would have expected that this fellow would go like this and maybe go down slightly, but what one is seeing is that it goes up and then comes down like this. This is K versus T, and this is what we want to understand, what causes this. And what would happen is that if you look at the scattering cross sections, what we have considered is, let us call it sigma total is sigma boundary scattering plus other sigma other mechanisms, and it is these other mechanisms that are causing this behavior where the conductivity comes down exponentially. And this also immediately implies that tau, the collision time being inversely proportional to the scattering cross section, you have 1 over tau is equal to 1 over tau boundary scattering plus 1 over tau other mechanisms. And therefore, tau is equal to tau boundary scattering times tau other mechanisms divided by tau boundary scattering plus tau other. So, if tau boundary is much greater than tau other, effectively the scattering time will be equal to tau other, and that mechanism will start dominating. So, therefore, what we are seeing is that after a certain temperature, the boundary scattering kept making the conductivity go higher and higher, but after a certain temperature, other mechanism is starting to dominate, and this is what we want to understand, and that is where the other mechanism here we are going to show is anharmonic. This arises from anharmonic terms in the potential. They cause scattering of phonons. How does that happen? So, remember, if I have this Hamiltonian, which is p square over 2m plus 1/2 k x square, in this we saw that this is a collection of harmonic oscillators n k plus 1/2 h cross omega k. So, all these phonons then they move around independently like waves in a linear medium. So, a wave comes in, other wave comes in, interferes and then goes on its own way. No scattering. But if I take the next order term, an harmonic term was g x cubed. Which is going to be proportional to q k 1, q k 2, q k 3, because each x has that q k e raised to I k x behavior, and this is going to be equal to combination of 3 creation and annihilation operators. So, let me write the first one a k 1 dagger a k 2 a k 3 plus a k 1 dagger a k 2 dagger a k 3 plus all of the terms, and it is this term that is responsible for limiting k thermal. How so? So, what this term indicates, the term a k 1 dagger a k 2 a k 3 is that 2 phonons of wave vector k 2 and wave vector k 3 get destroyed, and they create a third phonon of wave vector k 1, such that k 1 is equal to k 2 plus k 3. Because we have seen in the previous lecture that crystal momentum of phonons is conserved. So, this is what is going to happen. Now, let us see what happens if we mix 2 small k's and 2 large k's. So, this is the Brillouin zone, and suppose I have one small k and another small k, k 2, k 3, this creates a phonon of k 1. Mod k 1 lies still in the Brillouin zone. On the other hand, suppose k 2 and k 3 were quite large. Then and I will start making it from the center, the k 1 may go outside the Brillouin zone. So, in the upper case k 1 remains in the Brillouin zone. In the second case, k 1 goes out of the Brillouin zone. If that happens, we have learnt in the phonon case that I can always add or subtract reciprocal space lattice vector and bring it back in the first zone. So, in the second case, what is going to happen is that I have this k 1 which has gone outside the Brillouin zone, and I subtract a g. So, this from here to here is pi by a, and I subtract 2 pi by a, so that k 1 is equivalent to this. This is k 1 minus g, and in fact, it is going to be the other way. So, this is going to be not this one, but here. So, what is happening if I look at the picture that we make of Brillouin zone? There is this phonon curve, and I look at k at this point, and this we see is equivalent to k somewhere here. So, this is k 1 and this is k 1 minus g. In the extended scheme, this is where I am coming, it is somewhere here. This point is equivalent to this point, and for this k, omega group, which is v group, the speed of the group velocity, which is d omega d k, is less than 0. So, let us now try to understand what does all this mean. What it means is, if I have two large wave vectors k 3 and k 2, and they give rise to a k 1 which goes outside the zone, then the combined phonon starts moving the other way. So, let us write this. If two phonons with large k 2 and k 3 combine and give one phonon of k 1 equals k 2 plus k 3, then the new phonon is moving in the opposite direction. That is, its V group is less than 0. And this effect, the combining of two phonons to give rise to a new phonon, this arises due to the anharmonic term g x cubed, because it had that 2 annihilation and 1 creation operator. So, let us see what is happening if I make this Brillouin zone again. I had one phonon going this way, one phonon going this way, little different k, and they combined, these two combined and gave a new phonon which is traveling the other way. And this is known as Umklapp process. Comes from the German word Umklappen, which means to turn around. So, the anharmonic term in the potential can combine two phonons and make the third phonon go the other way. That means, if the energy was being taken to one side, suddenly these two phonons get scattered, and its effect is that their energy now is actually going the other way. So, this is a scattering mechanism that limits the conductivity of heat going one way, and that is the one that is going to give rise to that e raised to constant divided by t, and that is what I am going to show now. The scattering cross section for Umklapp is going to be proportional to the number of phonons, and this will come into play as temperature goes up, because then only high k phonons get excited. If only low k phonons are there and you get a phonon which is within the Brillouin zone, this, as opposed to Umklapp process, is known as normal or N process. On the other hand, if I have these two big k phonons and they combine to give a k which is going outside the Brillouin zone, this is the Umklapp process or U process. And this will come into play only if the temperature goes high. Why? Let us go back to the Debye argument, where we had a Debye sphere of radius k d, and at temperature T only these modes were excited at temperature T lower than theta Debye. So, now before I develop this further, let me ask you to do two things. First question I ask you is, for dispersion curve omega k, plot V group versus k. And see that on the left hand side of the origin, it is indeed is negative. The other question I am going to ask you is, if sigma Umklapp is proportional to photon and phonon, what is T dependence of sigma u for T much greater than theta Debye. With this, let us develop the argument further. So, now I have two mechanisms, and 1 over tau is going to be 1 over tau boundary plus 1 over tau Umklapp. 1 over tau boundary is nothing but 1 over the size of the sample divided by V sound, or some V, plus 1 over tau u is going to be some time t 0 times sigma u inverse. Now, sigma u is proportional to n, which is 1 over e raised to theta d divided by t minus 1, which at low temperatures I can roughly write as e raised to minus theta d over t, and therefore, 1 over tau is equal to 1 over d over V s plus 1 over tau 0 e raised to theta d divided by t. Tau effective, net tau is going to be therefore d over V s times tau 0 e raised to theta d divided by t divided by d over V s plus tau 0 e raised to theta d divided by t. For t tending to 0, I have e raised to theta d divided by t going to infinity, and therefore, implies tau effective is roughly d over V s, and this gives kappa proportional to t cubed d, as we saw earlier. Now, as the temperature is raised, e raised to theta d by t becomes smaller and smaller, and at some point it will become very small, and then tau effective will go to tau 0 e raised to theta d by t. Roughly, this could be theta d by 2, theta d by 3, theta d by 5, but that is the rough behavior, and therefore, L is going to be roughly V sound tau 0 e raised to theta d by t, and I can therefore write that after this initial boundary scattering, which was t cube behavior, I have kappa, which is equal to 1/3 C V, which does not have very severe t cube kind of dependence on temperature now, because T is going up, then some V tau 0 e raised to theta d by t. Remember, how does C V go? C V versus T is this t cube and like this. So, we are somewhere here, and therefore, this curve, I am going to go back here, is going to go up, and when you go to a little higher temperature where C V kind of becomes larger and weak, has weak temperature dependence, the only behavior you are going to see is this e raised to theta d by t, maybe e raised to some constant by t, constant could be theta d divided by something, but that is the kind of scale you are going to see. So, this is the behavior one is seeing, and this explains, the Umklapp process explains this behavior. Let me ask you a question at this point: how is T effective affected if theta d is very high. And when I say very high, the theta d diamond is 2000 K. How the mechanisms that dominate are going to change. So, this transition takes place at about maybe theta d equals theta d by 5, theta d by 10, but then it's the conductivity starts going down. So, Umklapp processes are rising due to anharmonicity limit the thermal conductivity and start making it become smaller with T increasing. So, it's a mechanism, it's a scattering mechanism that comes into play as you raise the temperature, and that scattering mechanism that limits the conductivity. Now, what happens as temperature goes further up? As T goes further up, then N is going to be 1 over e raised to theta d by T minus 1 is going to go as T over theta d. And therefore, tau scattering due to Umklapp is going to go as theta d by T. And at such temperature Cv has gone to 3 R. So, you are going to have kappa equals 1/3 3 R times some velocity quantity. It need not be V sound, because now we are exciting K's which are way above the linear regime, but more important thing is that you are going to have a tau which is theta d by T, this is V square. So, kappa is going to go as 1 over T. So, if you were to plot this thermal conductivity versus temperature, you are going to get a 1 T cube behavior, then it is going to make a transition, then you are going to see some e raised to theta d by T, and then it becomes a straight, this is -1 slope, and this is e raised to some constant over T. We can write this as e raised to theta d by T, and this is T cubed. The behavior has been explained. So, let me write here that when we say high or low temperatures, the scale is provided by theta d. So, T low implies T over theta d is much less than 1. T high implies T over theta d is much greater than 1. So, that is the kind of natural scale for temperature here. So, we have taken care of boundary scattering, we have taken care of scattering due to phonons of scattering of phonon due to phonons, and gotten this curve. The final thing that we need to learn about is impurity scattering. So, let us see what happens in that case. So, what we have learned is initially we are having a behavior which is T cube, and at this low temperature the dominant lambda phonon at low temperatures is proportional to T inverse. Let us show that. So, for that I want you to recall that at low temperatures, that is T much less than theta d, the Debye sphere is filled up to k, which goes as T. So, this is from a previous lecture. This is the Debye sphere where the largest radius is k d, and at temperature T you have only a small portion of its filled, where I will write this as k at temperature T is k b T divided by V sound, and then you divide by h cross. And therefore, lambda at this temperature is 2 pi over k T, which comes out to be h V s over k B T. So, smaller the temperature, larger wavelengths are going to be dominant. And what happens at larger wavelengths? These phonons get scattered by these impurities, again a scattering mechanism. So, phonons get scattered by impurities. At low temperatures, large wavelength phonons dominate, and their scattering cross section is proportional to 1 over lambda raised to 4, and at this point I would like you to recall Rayleigh scattering of light and explanation of blue sky. It's precisely the same mechanism. There are these long wavelength vibrations that are getting scattered by these impurities, and therefore, I have shown that lambda at t going to 0 is proportional to 1 over t, and therefore, scattering cross section due to these impurities is proportional to t raised to 4, and therefore, tau is proportional to 1 over T raised to 4. And therefore, at such temperatures, the thermal conductivity, which is 1/3 CV V square tau, is going to be proportional to 1/T. So, if there are impurities in the system, even before Umklapp process sets in, this is going to go as T cube initially and then go down as T inverse. Whereas, with the Umklapp process, this goes up further and then Umklapp process is set in, this starts having a behavior which is exponential and then becomes linear. So, this is due to impurity scattering. Finally, at high temperatures, both the Umklapp scattering as well as impurity scattering give T inverse behavior. So, at large temperatures, conductivity is going to go down as 1/T, and in between the temperature between 0 and theta d, the behavior is going to be slightly different. Now, impurity scattering would also not let the conductivity go very high. So, initially you have boundary scattering, T cube behavior, and then impurity scattering sets in and then it starts reducing the conductivity. So, for this also let me then write, if all these three mechanisms are talked about, then you are going to have sigma equals sigma boundary plus sigma Umklapp plus sigma impurity. Tau is going to be tau boundary, tau Umklapp, tau impurity divided by tau boundary, tau impurity plus tau boundary, tau Umklapp plus tau Umklapp, tau impurity. Depending on which one is the smallest, that is what is going to determine the, that is what is going to limit the thermal conductivity. So, let me ask you a question here again, and I made a comment on this earlier. What will be the thermal conductivity of a pure sample, and what will limit it? So, with this let me conclude the lecture. So, what we have learned is, 1, effects of anharmonic terms in interatomic potential have been studied. 2, we have shown that x cube term is responsible for thermal expansion. 3, we have shown that thermal conductivity of pure samples is limited by anharmonic effects that give rise to Umklapp processes, and 4 various scattering mechanisms for phonons have been discussed qualitatively. Thank you.